for squeezing me in on this tight schedule. Okay, so I'm going to talk about average number of zeros of characters of finite groups. As we go, we'll see what that means. It's quite a mouthful, but it's nothing really. Okay, so I'm going to start off with some notation, maybe recall some few things, and then we get into character tables right away. Right, so when we say, well, a set of irreducible characters will be represented by IRR of G, as Mandy showed us when she presented. And then the character degree is just the character value on the trivial element. And if the character value is equal to 1 on the trivial element, then the character is called a linear character. And then chi is always invariant on conjugacy classes, so when you create the character table, you'll see that for each conjugacy class, there's only one value of a character. Right, so we know that every finite group is an associated character table, and the question that we are asking is, how does the information of a character table of a particular group affect its structure? Basically, what kind of information can we extract from a character table? And this is inspired by Brouwer, as Mandy showed us in the morning, but this is what we are going to talk about is much lighter than what she was talking about. Right, so we get on to average character degrees. So the question that, so the motivation of what I looked at is based on the average character degrees of a finite group, and so this was introduced by Magad and Tong Viet, where they were looking at something totally different, and then people then formalized it to become these. And these are basically, so the average character degree of a group is basically the sum of character degrees over the number of irreducible characters. Right, so just as examples, if you've got an abelian group, then its average character degree is going to be is going to be equal to 1, because all the characters are linear, so therefore you just count the number of characters that you have over the number of characters, so it becomes 1. And for A5, it is 16 over 5, and then for A4 is 3 over 2. If you just look at the character table, or if you look at the character degrees, you can easily calculate and find that. Right, so the question is, can we say something about a group if we know something about its average character degree? And the first result in this direction was from Magad and Tong Viet, which say that if the average character degree is less than 2, then the group is going to be solvable, right? And they use the classification of finite simple groups to show that this is true. And they conjectured that the bound should actually be 3. I don't know why they picked 3. I think they were very conservative, but I don't know what was their thought process. But anyway, Isaacs, Lukács, and Morito then showed that their theorem, their conjecture is actually true. And in that same paper, they then put a bound for a group to be supersolvable, and if it's a group of odd order, to also be supersolvable. So you see that the bound for a general finite group, there would be less than the bound for groups of odd order. And they also gave a bound for nilpotency. Right, and in that paper they also conjectured that actually the bound for solvability should be 16/5, which sort of makes sense because the average character degree of A5 is 16/5, right? And then in the next year, Morito and Nguyen then proved that the conjecture holds. And so all the results that I've presented, the bounds are optimal because we've got all these examples that show us that that is the case. Right, so the question, so I thought about it and said, well, I've done zeros of characters in my PhD. Can we get sort of results that are like this for zeros of characters that we find in character tables? And so I'm just going to talk briefly about what are zeros of characters so that it's clear. Right, so if you've got an irreducible character of a finite group and you've got an element G, then we say if the character value is equal to 0, then it means that the character vanishes on G, right? And this becomes a zero of character. So it's like on that element, if you look at the character table, we expect to see 0. So those are the zeros of characters. That's where they're coming from. And then, so for linear characters, this is, you will not find this character value because if you look at if you map a group onto the general linear group, that's how you find a character. And so if you map a linear character, it has to go to the complex, the non-zero complex numbers. So instead of it being like a GLN where n is greater than 1, it will be 1. So therefore, it's just the complex character. So therefore, you're not going to get a 0. But then Burnside in 1904 proved that if the character is nonlinear, then there's always going to be a 0 of character, of that character. And I mean, this has been generalized in many ways. Right, so now we get on to what we want to talk about. So I then defined an average number of, the average number of zeros of characters of a group by saying that will be the number of zeros that we find in a character table over the number of irreducible characters that you have, right? And then, so I asked the same question that they asked, well, that is asked, okay, I'm coming back to the example. So the question is, how does the average number of zeros of characters affect the structure of the finite group? And I just put here examples of character tables. So for A5, we can see that there are 5 zeros in that character table, and we've got 5 irreducible characters there, so therefore the average number of zeros will be 1. Same applies to S5. If you count the zeros there, there should be 10, and we've got 7 irreducible characters, so therefore the average number of characters of S5 would be 10/7, right? So we asked this question, and it turns out that if the average number of zeros is less than 1, then G is going to be solvable. And the bound is optimal because of our A5 there. And the proof of the theorem, so I had to reduce the problem to almost simple groups and then use the classification to prove that almost simple group will have average number greater or equal to 1. And so the classification comes into play when we prove that I looked at groups, almost simple groups with an irreducible character that vanishes on one class. And so if you want to think about it, what it means is, so if every irreducible character has more than 2, then we most likely are able to easily show that the average will be greater or equal to 1. So the ones that might be a problem are one where there's one character, where there's a character that vanishes on one class. So I looked at those and then saw that, again, all of them are greater or equal to 1. So that's the first result. And then I went on to look at super solvability, and again, so the bounds are guided by the groups that gave us optimal average character degrees. So again, so I looked at the average character degree and saw that, okay, for A4 is half, so if it's less than that, then the group should be super solvable. And so we proved that. And then when we looked at nilpotency, something weird happened, which is that not only will the group be nilpotent, but it will actually be abelian. So there, if someone, following what Mandy said in the morning, if someone throws you a table with a bunch of values, and then you see that the average number of zeros is less than a third, but the group is not abelian, then it's not a character table. Basically, that's what it means. Right. And then for odd order, we follow the same, because you saw that in the case of average character degrees, the bound was a bit higher. So in this case also, I looked at that and then saw that, okay, if the average number of zeros is less than 1, then G is going to be super solvable for groups of odd order. But that was not the best bound. And then I said, well, it should be 16 over 11. And 16 over 11, again, is guided by the group which is optimal for average character degree. So the group is the group of, the non-abelian group of order 75 is the one that has those properties. Right. Anyway, so that's what I did. And then later on, Morito then came into play and said, well, I can actually classify all the groups that have average number of zeros less than 1. And so he wrote a list of it, and this proof used a different approach. I don't think I'll talk about it, but yeah, to show solvability, he used a different approach. And okay, so I'm not going to talk about the proof, but just know that he used a different approach to prove it. And then he went on to look at the super solvable groups and showed that the conjecture holds, and he in fact showed that there are only 4 non-abelian groups of odd order that is this property. So my conjecture was gone a year after I proposed it. Right, and then so that's the story on average number of zeros of characters at the moment. Well, technically not quite, but okay, so there's a paper I'm reviewing where someone did a bit more, but I can't talk about it since it's under review. Then Morito, he looked at his problems that, he looked at his classification and saw that for average number of zeros less than 1, you can actually bound the fitting height of a solvable group. And then his question was, well, is this true for any solvable group? That's one question that he proposed. And then another interesting question might be, is there a relationship between the average number of zeros and the average character degrees of a group? And so those are two open questions there. There are a bit more, but I just put these two here. And that is it. That's all I have for you.